Hey y'all, I'm back with another video. Today we are going to be doing a fixed charge integer program problem. I have 3 pages of this textbook problem, and it's nice because it has the solution at the end, so we can see that when we run it in Python we get the right answer. But basically I'm going to go through this and summarize the problem so that you don't have to sit and read it all. But if you'd like to pause the video, definitely do that and try to understand the problem more. So basically in this problem there's 3 types of clothing. There's shirts, shorts, and pants, and each clothing has a certain machinery required to make that, and that machinery has an associated cost. So for shirts it's $200 per week, shorts is $150 per week, pants is $100 per week. And then there's also a max of 150 hours of labor and 160 square yards of cloth available for each week. And then what we want to do is maximize the profit. So right here it shows you the decision variable we'll be using for the amount of each product produced. Then this table is the labor that each different type of clothing requires, and then the cloth that is required to make that. This next page, there's a table right here. It's the sale price for the all the clothing, the cost for all the clothing. So then we also have this other decision variable, and the reason we have that is so that the cost of running the machinery is not included if we don't produce that type of clothing. So we need to have this binary variable so that like down here it gives the equation for the cost of running the machinery. So if no shirts are produced, then y is going to be giving us 0, and then this machinery cost will not be included. So there's y1, y2, y3 for each clothing, and then let's see what else. So then down here is our profit equation. So basically it's the sale prices for each clothing minus the cost for each clothing, and then minus the decision variable times the weekly renting machinery. So again, those will only be included if those type of or that type of clothing is produced. So then this is just the equation when you subtract all of that, and then we have a couple constraints. So the first constraint is the labor constraint. So we add up all of our labor requirements for each variable, and it has to be less than 150 hours a week. And then over here's our cloth constraint. So the max is 160 yards, I think it was, times, or is supposed to be greater than or equal to the sum of the amount required for each clothing. And then I think that's pretty much it. And then this is exactly what we're going to use in the computer. But if you don't do this part, then our x and our y variables are not going to be tied together. So we do need to include these equations down here, and I'm going to go ahead and explain that. So basically what these equations do is they make sure that if x is greater than 0, then that associated y will also be greater than 0. Or it'll be assigned 1 if this is greater than 0. So I think it says it right here. Whenever xi subscript I is greater than 0, y subscript I equals 1 must hold. And the reason that we also have this m1 variable, which is really just a large positive number, if you had just ignored that and just said x1 is less than or equal to y1, then if we had 20 shirts created, that would not be less than or equal to 1. So what we need to do is we need to figure out the max amount of shirts, shorts, and pants that can be produced, and they already did it for us. They told us that the values, when you figure it out based on the amount of labor and the amount of cloth required, and what we have already, or the amount that we can use each week, it gives us that M1 equals 40, M2 equals 53, and M3 equals 25. And then I think this just further explains it. And then that is our solution down there, and I'm going to show y'all how to get that. So I am not going to type out all the sets and the parameters like I normally do. So we want to start with from PuLp import, asterisk, and then I'm going to copy and paste and explain all these. So these are our sets, or set. So we have, I guess we could call that product, not shirts. So we have product 1, 2, and 3. You could also say like shirt, but that's just going to take longer. I like to type out the numbers instead, especially since they already show us these subscripts and I can just follow along with this. So this is our set of products. Then we have this labor parameter. I'm just going to type parameters to organize. For the shirts, we want to do the 1, colon, and then whatever our labor requirement is. We're going to do the same for the cloth, and the price, and the cost. So obviously this is our only set, so that's the only thing we will be using within our dictionary. So we want one for labor, cloth, price, and cost. And then we also want one for machine. So that is the cost of using that machinery type, and then this last one is our restriction for our M values, and I still associated that with the 1, 2, and 3 since that's our only set. So then now that we have our sets and parameters, the next thing we need to do is make our problem variable. So we say prob equals LP problem, and let's just call this fixed charge. And then our what we're doing is we are maximizing the profits, so it's LP maximize. And then next we want to write our decision variables. So first we do our X variable. I'm just going to say X underscore vars equals LP variable dot dicts, and let's just call this produce. And then the set we refer to is our product set. And then this is an integer program, so we want to say our lower bound is 0, and then because it says that, let's see, right here, it says x is greater than or equal to 0, and then it's integer. So we want to say 0, upper bound none, and it's an LP integer. And then next we have our y variable. My dog is chewing on something in the background. Okay, so our y variable is binary, so let's just say manufacturer is the name. And for binary variables, we do 0, 1, and then LP binary. Next, we need to do our objective function. So we're going to set that to our problem variable. So we say prob plus equals LP sum, and let's look at our equation that is already given. Let's see. So it's maximizing the. I think when I did this, let's see. They already simplified it, but I'm gonna type out everything since we already put these parameters in. So basically, you want to do price and indexing it with I in brackets, and we're gonna say price times the only variable we're using right now is the x vars, and then for I in prod. And then we are going to subtract the sum of our cost, index I, times the amount that we produce of each type of clothing. And then we are also going to subtract the manufacturing cost. And I'm going to move that over. So we have our binary variable to determine whether or not that cost is included. So y underscore vars I times machine I, and we're going to say again for I in prod, and I just realized I forgot that here. Let me move this over. And then next we need our constraints. So let's look at our first constraint. Don't think it was on that page. This is it's all over the place. So our first constraint was our labor constraint, and we already have our labor parameter. So we do summing over, let's see what we're summing over. Labor index I times our X variable. So the amount of labor required for each product is what we're summing over. And that needs to be less than or equal to 150. And then our next constraint is our cloth constraint. And I'm just going to put labor constraint. So we're going to sum over the cloth required for each product. So you do cloth index I times the X variable index I, and we put our loop in the same line since we are summing it over. And then that needs to be less than or equal to 160. Cloth constraint. And then our other constraints are down here, and what we need to do for that is we actually need to start off with a loop. So we need to say for I in prod, so that it does, this equation is fulfilled for each type of product. Since we're not really summing over anything, we're just using this equation for each one. So that's why we can use a loop. So for each product, this equation must hold true. So prob plus equals, and we're going to just say x underscore vars I for I in prod is less than or equal to our restrict, that's our m value, I, and you can look at the subscripts and see why I'm using I for this, and then that's multiplied by the y underscore vars I, that also needs a subscript, and this side also needs the loop. Oh wait, I'm sorry, I apologize. These both don't need the loop. We already did the loop. We're not summing anything over. I'm just used to doing that all the time. So for each one of these products, this equation has to be true. And then finally, we are just going to do our prob dot solve, and I'm just going to copy and paste this. So you want to say for v in prob.variables, parentheses, colon, if that variable value is greater than 0, then we want to print that variable name and we want to print its value. And let's just say total profit, and then comma, value, parentheses, prob.objective is how we print our z value. So let's go ahead and see if this runs. We're going to call it fixed charge. You can call it whatever you want. So I spelled variable wrong. Oh, on the other one. Let's see. Alright, so then we have down here, we can see that our z value is 75. Our x3 value, the reason it says manufacturer underscore 3, that's because we named it that, but I could have just said x or y. That might have made it a little bit easier to see when we print it. Let me just show you that really quick. X, y, just makes it easier for comparison. So we can see that our solution is correct and that our z variable is equal to 75, our x underscore 3, that's our x subscript 3 is 25, and of course our y underscore 3 is equal to 1 since we are producing pants. And hopefully you guys were able to follow along, and hopefully it wasn't too all over the place with all the different textbook pages. But again, I'll link that textbook below in case you happen to want to go look at it yourself. Bye!